Okay, hi. I think this is recording audio, so hopefully it is, so I don't go through this whole thing without audio. But so it looks like we're looking at bonding, which should be really easy once I explain it, and then nomenclature, which honestly we don't focus on this much anymore. We know certain names, but it's pretty much just memorization with that and practice. So I'll just try and go through everything, and then at the end I'll look at some of the practice problems that you sent me, so you can just fast forward to that if you need to. Okay, so here's a warm-up question. I know that you guys probably already did this, but it's good practice. So you're looking at calcium, which is abbreviated Ca, and I'm guessing you'll get a periodic table, and then chlorine is Cl. And I realized I should have opened a periodic table before this, but I'll find one eventually to use, just to look at. I think I'll pull it up on my phone right now, actually. Just to reference. I would say that it's always good to have a periodic table next to you because it tells you everything about valence electrons and charges and everything like that. That's really important to know. So yeah. Highly recommend having that with you, or even just like ripping it off of the back of your exam. Okay, so for calcium just naturally on its own has a 2+ charge. Sorry, we do that in orgo. And you can tell this because it's in the second row of the periodic table. Now, calcium also has calcium also has 2 valence electrons, which I'm just going to abbreviate electrons like this, and then in the future I'll just abbreviate valence electrons like this. So the 2 valence electrons that you draw electrons as 2 dots, which I'm sure that you know. So that's calcium. And then chlorine is in, so for counting for like the charges and the valence electrons, you just count across the top, but you skip rows 3 through 12. That's like all of the metals and stuff on the periodic table. So the first row, so chlorine is in the 1, 2, 3, 4, 5, 6, 7th row. And so we know that it's going to have all of those valence electrons. So it's going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. And sorry, I don't know how to do the charge here. I need to look at your notes. Okay, so it looks like it restarts here. We never really learned it this way. We just had to memorize it, but I guess it's 1, 2, 3, 4, so it matches up to here, but then when you get to the 5th row, it becomes 3, 2, 1, 0. So since chlorine is in the 7th row, it's going to have a -1 charge, which we can see there, but you can just draw that as like a -1 or just a minus sign if you want to. And then looking at chlorine and calcium, this is kind of tough because in orgo we always say that we want to fill an octet. But here, calcium has the worst charge. It's a positive charge. And so it's going to want to get rid of that positive charge to become neutral. So calcium would most likely want to grab onto 2 electrons. I'm not quite sure about this, so I could be wrong. And then chlorine is going to want to bind to something else, because if it binds to something else, so look, we've got 7 electrons. Let's say that it binds to like a hydrogen, which should have 1 electron. If it binds to this, so basically these two are coming together to form a bond, so you'd have Cl and then H. And I don't know if you guys draw your bonds like this. You might draw them like this, or you might draw them like this. I think this is easier, but it's fine either way, and I think your professor or teacher had done it this way, so I'll just leave it like that. But if we look at this, when we're counting octets, you count all of the electrons in the bond towards each atom. So this fills chlorine's octet while getting rid of that -1 charge, so it makes it neutral. So you're always wanting to make the atom either neutral or a filled octet. Oh, and we already did the charge, so that's fine. Let's see how we did, because I'm not sure. Oh, I don't know why it says it wants to lose 2 electrons. Well, this would make sense because it's going to want to gain the 1 electron with the bonding like I talked about. I think that the explanation for this, and again, I haven't done this in a long time, we don't really use calcium in many reactions. It's not a very useful element, I guess. But I would guess that this is because in each shell you have, I think it's 2 in the first shell, and then, so 2 in the first shell of electrons, and then you go to the outer shell, and it's 8. So if you take these 2 away, it would form an octet. So that would be my explanation for that, but I'm not quite sure. Sorry, I haven't done it in a while. And then, well, this is just stuff that you should memorize. And if you have this memorized, it's pretty good. These are pretty easy to remember because it's just 1, 2, 3, 4, 5, 6, 7, and you just skip the lower part. And these guys are weird, the halogens. It's just 2 valence electrons and then 8. Or, well, this is helium, sorry. I think. Hopefully it is. These are the halogens down here, and they all have 8 valence electrons. So, like, bromine would have 8, and you would draw it like this. And then I don't know if you're going to be tested on this, but these are just the different types of elements that you have. So, nonmetals are going to be hydrogen, and then everything in this kind of staircase, whatever, plus helium. Metals in blue, and then metalloids, which are kind of different, in the orange. All right. It says it's review, so you should probably already know. But this, you can just memorize this stuff. Yeah, cation and anion just means positive and negative. But the nonmetals would rather be negative, and the cations would rather be, they'd rather be positive. And one thing we can look at that I saw they talked about earlier in your notes, and I'll erase some of this just for clarity so that we don't have so much stuff on here, is that when it comes to terms of electronegativity, which just means how well can an atom support a negative charge, essentially, that the general trend, now this doesn't apply to every single element, so it's something that you should just kind of be aware of in general, but the general trend for electronegativity is that it goes from down here on the periodic table up to here. So as you move in this direction and up, the electronegativity, which I'm abbreviating as EN, that increases. So that's something that you can kind of remember. Just means that, like, we'd have calcium here, and I think oxygen here. I don't have it memorized, but I think that's how that goes, or maybe it's this way, I don't remember. But this means that calcium would be less electronegative than oxygen, so oxygen would be more likely to be negative, and calcium would be more likely to be positive when you're comparing those two elements. But we can get into that more later. It's just a general trend to remember on the periodic table. Again, this is just kind of, yeah, and then metalloid. I feel like if you just memorize this information, it's, like, fine. And just then applying that information. We've already practiced some Lewis dot structure. That's kind of what we did with chlorine. If you remember, it had 7, and calcium had 2. You just remember this. Basically, you're looking at, the valence electrons, which is what we already did. If the outer shell is, and this isn't really necessarily true when you get further in chemistry, but for the case of your course, it is. So if the outer shell is full, so it has 8 valence electrons, if it's like a noble gas or a halogen, I think, it's stable and it won't bond. So if we go back to the periodic table, I think, let me pull up my periodic table because I can't see it and I feel like I'm getting things wrong. Oh, bromine is over here. That's why I was thinking wrong. So bromine would have 7. Ignore what I said earlier. But let's take neon for an example. because neon is a noble gas. Neon it has a full octet, but then it also has, it also has no charge, so this is neutral. It's not positive or negative, neither of these. And so because it's neutral, so without a charge, and because it has a full octet, and when I'm referring to octet, I don't know if I have explained that, but it just means that it has 8 electrons. That's how most electrons are happiest, just because you want to fill the valence shell. The valence shell is the outermost shell of the electron, so you can have of the orbitals of the atom. So let's say we have bromine. I'm not exactly sure how this would be, but let's say there's always 2 in the first, I believe. Anyways, all that we're worried about is the outer ring. So like there's a couple of rings in here, but the outer ring is your valence shell. And that can hold up to 8. And so in something like calcium up here, well, that's not really a good example. We'll do chlorine. Chlorine would have 7, 1, 2, and you can kind of draw a ring and think about it this way. So you want 8 in that outer ring. And so we have 1, 2, 3, 4, 5, 6, 7, but then this spot is open, so you'd want to fill that up. But if that confuses you and it's not something you need to know, then don't worry about it. But yeah, so it's good to know that noble gases, so in this last row of the periodic table, are very, very stable, and they're not going to react with anything. And then that all other elements want to be like the noble gases, so they want to be neutral and have a full octet. And then the hydrogen and helium are weird, but if you just remember those, they just need 2 electrons because they're in the 1s2 electron configuration. So hydrogen on its own just exists with 1 electron normally and a positive charge, so it's ready to bond with other things like chlorine. So chlorine can just pick up this hydrogen with its electrons and then form a bond with that to give and remember we count in the bond, we count that as 1, or we count that for each element, so that gives the hydrogen the 2 that it needs. And then helium is the same. It's just in a weird spot on the periodic table. And then Lewis dot structures, they're again just kind of looking at the periodic table and the trends in the periodic table, so that's all the numbers up here, and just knowing how to draw those. So everybody here is going to have 1 valence electron, so you just draw 1 dot, 2 here, 3 here, 4 here, 5, 6, 7, and then 8 for all of these, but then 2 for helium up here. And that's just kind of how they naturally exist, and then you can determine whether or not they would want to grab an electron or not based on that. And one thing you can remember, if you're having trouble, a lot of the most common elements are going to be hydrogen, carbon, nitrogen, and oxygen. So a rule that you can use is something called the Honc rule, H-O-N-C. So if you just remember that hydrogen, so in Honc, we're just saying that this is how you spell it. You're spelling it with a C, but it's like an abbreviation. Hydrogen is the first one, and then oxygen is the second, nitrogen is the third, and carbon is the fourth. And this has to do with bonding, but it also gives you a hint of how many electrons it's going to pick up. So hydrogen likes to form 1 bond, and if we think about that, hydrogen making 1 bond, that gives it the 2 electrons that it wants. Remember how we talked about that? And then oxygen, it wants to make 2 bonds. So let's say it's bonded to a carbon. That would give it 1, 2, 3, 4, 5, 6, 7, 8. So that gives it a full octet. So 2 bonds here for 4, 5, 6, 7, it's for 8 electrons total. And then you go to nitrogen, and it's the same thing. It can make 3, and then have 1, 2, C. We'll just say that it's bonded to a C for that, and then that gives the nitrogen 1, 2, 3, 4, 5, 6, 7, 8. and it also gives it 5 electrons to make it neutral. It's happening here too, to make them all neutral. And then same thing with carbon, but carbon usually doesn't, it's not really possible to have a bond that's like 4 like that. So carbon will usually see like maybe bonded to an oxygen, and then it has like 2 other things coming off of it, or it's just bonded to 4 other things. But that's just something you can remember for bonding. We just talked about the octet rule, just because it wants to be like the noble gases and really stable like that. We talked about this. This is the octet rule. I don't have room to write, but that's okay. Yeah, and then metals are going to lose the electrons, so they're going to donate them, and then nonmetals will gain them. And then this is ionic versus covalent bonding. Ionic bonding is where essentially this calcium is just donating straight in to the the calcium is just donating its electrons to the chlorine, or you can think of the chlorine as taking it. So these electrons are just going right there, and they're leaving the calcium entirely. So the calcium is just on its own now. And then the chlorines have their full octet. And if you remember what I said earlier about it having 8 electrons in the next shell after the valence, I don't know if that's super important for you to know, but that's ionic bonding. So it's like basically this one, the chlorine is just stealing electrons from the calcium and leaving it with none. Covalent bonding, though, is shared electrons. So here we have an oxygen that has 6 electrons, and it wants to make a full octet. So these hydrogen electrons are going to come up here and bond. But you can also kind of think of it as these are attacking here too, because there's a positive charge on this hydrogen, if you remember. So this is also kind of attacking. And you don't have to draw all these arrows when you're doing it, but you can kind of just think of it. And then you can draw the bonds like this rather than as 2 dots. And it shows that those electrons are covalently bonded. Sorry, that looks messy. It shows that they're covalently bonded, which means that they're sharing those electrons. So if you just remember ionic, it's like they're stealing the electrons not shared. And then the covalent is sharing. And we just kind of talked about this. I described it. This stuff is just memorization. I don't really know how to explain it to you. It's just rules that you can memorize. Yeah. And so that's basically I said it was stealing, but it's, the transfer of electrons, so gained or lost. So, and I think this was something you had a question about, the gaining and losing of the electrons. Let's look here. So here, if we look at it, the chlorine, I'm going to draw this, your teacher has it really blurry, so I'm going to draw it again. The chlorine has 7 again, we've done that a bunch, and then the magnesium has 2. And if we think about the electronegativities of this atom, looking at the periodic table, which I don't know if you have one next to you, but magnesium is more likely to support a positive charge, and chlorine is more likely to support a negative charge. Chlorine also has 7 electrons, so it is much, much closer to having a full octet than magnesium. Magnesium is going to take 6 more electrons, so it's much more stable for the chlorine to just pick up one of these electrons here, and then the magnesium to donate that in, because the magnesium then becomes a positive charge, and then the chlorine becomes a negative. But technically, since they're ionically bonded, they're one compound, even though you can split up these charges like that. So I think magnesium should already have a plus charge here. I'm not sure why it doesn't. So when the chlorine gains that atom, it goes from neutral to negative, as you can see down here. And then the magnesium goes from a positive charge to a positive 2 charge because it lost an electron. And then those two are ionically bonded. Here's another warm-up. I don't know if you want me to do all these, so you can just fast forward if it's like things you already know. Let's see. So potassium is K, and then phosphorus is P. And I'm going to do some counting here. So this is in the... I really should have a periodic table with me. Let's see. So potassium is in the first row, so it has a +1 charge and 1 valence electron. So it's going to have a plus here, and then a valence electron. And then phosphorus is in the 1, 2, 3, 4, 5, 5, the fifth row. So it's going to be 1, 2, 3, 4, 5 electrons. And sorry, I have to think about this for a second. And I don't know that that's going to have a charge on it. I think that's a neutral. So if we remember that potassium is in the first row of the periodic table, which you can see on that. And so that means it wants to have 2. It wants to have 2 electrons. And if we look at that, giving it the 2 electrons is going to make it more positive, or it's going to take away that charge, and it's also going to give it a full outer valence shell. Whereas potassium needs, let's see, 1, 2, 3 electrons to fill that shell. This one only needs 1 electron. So what's going to happen is one of these electrons from potassium is going to go and attack, or one of those from phosphorus is going to go and attack the potassium. And then what you're going to end up with is a neutral potassium with a negative phosphorus. And this should be right. It may not be because you guys are in a different class and we do things differently, but the phosphorus is going to give... maybe the phosphorus has a positive charge. I gotta think about this. We're going to double check because I'm not 100% sure. Oh, so they're showing a bunch of... Wow, that's kind of... Sorry, they should have told you that they had 3 equivalents of potassium, because that's not really fair to expect you to. But basically, this whole process is just going to happen 3 times so that they can all be bonded. So you would show... Yeah, I'm not really sure why your teacher did it this way. But I guess you just have to know that it happens 3 times, which is stupid. But we can look at it this way. So the potassium will have 2 electrons here, and then 1, 2, 3, so we'd have K, K, K. So we can count this as 2, if you remember. So this gives everybody a full octet. So you have 2, 4, 6, 8 here. So that gives potassium 8. And then we remember that, sorry, I keep calling it potassium because of a P. It gives phosphorus 8, and then the potassium, it gives it 2, because we remember that potassium doesn't follow the octet rule. It has 2. And I guess that your teacher doesn't tell you when you have multiple equivalents of things, so I would just assume that you have an infinite amount of each of these, unless said otherwise, and that they can bond to each other many times. So you don't just have 1 potassium, you have a bunch of it floating around in solution, and you have a bunch of phosphorus, and those phosphorus are just going to pick up 3 potassium each, or the electrons from the potassium are going to go attack the phosphorus. That's really messy, but you can imagine it like in a flask, like that, and that's your solution. Because I guess your teacher doesn't want to say things explicitly. Okay. Covalent bonding, we already talked about this, how the electrons are shared. Essentially the same concept of you're forming a new molecule out of separate molecules in order to fill octets and make neutral atoms. If you're thinking here, this would have a positive charge, this would have a positive charge, so you're wanting to change that. And I believe oxygen would have, let's see, 1, 2, 3, 4, 5, 6. I want to say it would have a minus. It might be neutral, I'm not sure. That would be neutral, never mind. But anyways, these guys are going to want to come here because that'll fill it and make it 2. You can kind of see a representation of the valence shells here. So if this is the outer shell for oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8. And then for hydrogen, you have 1, 2, 1, 2, filling each one. So everybody's happy and everybody is in that halogen, or no, I keep saying halogen, noble gas-like state. So they're neutral and they have full octets. That's the key thing here. And then just remember with covalent bonding, what we just did earlier with the potassium, that was ionic bonding. So even though this exists as a compound, you can really kind of view it as like a K2 plus and then a P2 minus. And then together that compound is more neutral. And that might not be 2 minus exactly, but you get the point. And then these are types of covalent bonds. Pretty straightforward. It's just the same idea, just that, you know, the bonds are going to maybe form doubly or triply. So single bonds, we've already done that. Double bond, it'd just be like here. As you can see, this is bonding here, and this is bonding here, and same here, and this gives everyone a full octet. If you remember, carbon likes to have 4 bonds, and carbon likes to make 4 bonds, and oxygen likes to make 2 bonds. That's what I talked about with the honk rule. And then phosphorus is going to create those 3 bonds so that each electron can have a full octet. So we'd have 2, 2, 2 for this atom, and remember we count the bonds as if they're each one of the own. So like for this one, we would count all of these bonds as 2 electrons for that. So it'd be 2, 4, 6, 8, 2, 4, 6, 8. So it makes everybody happy. It's all about just keeping the molecules stable. And then that's just what they look like. Pretty straightforward. Oh, and you want to note that single bonds are the weakest. They can be broken easily. And there's also free rotation around those. You don't need to know that, but they can rotate essentially. And then triple bonds are the strongest. And I think this just really makes sense physics-wise. If you have, you know, an elastic string and it's just one supporting, maybe we'll draw like this, supporting like a heavy block, it's much more likely to snap than if you have 3 cords holding up a block. That's just basic physics and stuff. But yeah, a triple bond is the strongest and a single bond is the weakest. Bond polarity, we already talked about electronegativity. That's that trend that goes like that on the periodic table. And EN values she'll probably give you. So she'll say, you know, is this molecule polar or not? And she'll probably give you the numbers, and no matter what you subtract it, you do 4 minus 2, it's 1.9, greater than 0.5, that means it's polar. And if not, then it's not. So if it's greater than or equal to 0.5, then the molecule is polar. And that basically means that there's a different distribution of charge. Basically, the electrons, they aren't really just like stuck next to an atom. They're kind of like floating around in these clouds that we call orbitals. So with that, the most electron density, because remember, electrons are always negative. And fluorine is much further on the periodic table over here than hydrogen. Hydrogen's like over here. So that means it's a lot more electronegative. It can support that negative charge. So we can draw, this is a Greek letter called delta, and that's a negative. And then this is delta positive. So since fluorine can support that negative charge much better than hydrogen, the negative charge is going to go over this way. And I just drew this arrow to represent that negative charge going towards the fluorine. And so since all the electrons are kind of staying over here, makes it really negative over here, and it makes it really positive over here. Hopefully that makes sense. Kind of another drawing of that down here. This is essentially the same thing, except for we have the values. We know that this is polar just from looking at the electronegativities of the atoms, and then mathematically we can calculate that by doing 3.5 minus 2.1, and we already know that that's going to be greater than 0.5. Yeah. And it makes the orbital bigger too. So you can see that it's much bigger here than on the other hydrogen. Sorry, this is getting messy. Yeah, that's what the delta negative is all about. Essentially what I just explained. I feel like that's pretty straightforward as long as you can remember those trends in the periodic table and then be able to kind of draw those partial positive and negatives, which are these right here, the delta positive, delta negative, delta positive, and then the arrow pointing towards the more negative atom. Talked about this again. This doesn't make much sense the way that she explained it, because in this it's very obvious that you have delta positive on one side and then delta negative on one side. So it's a lot more, all the electrons are going to be over here. It's going to be a bigger shape and then a smaller shape here. I feel like that's pretty straightforward when you're looking at that. And then these hydrogens are smaller atoms here. So they're going to all kind of bend down while the nitrogen and the oxygen are going to bend up, just because they're bigger atoms. And they're not necessarily symmetrical either. My Apple Pencil might die, so that might be a problem. I might have to finish recording later. But I feel like that's pretty straightforward. But when she's saying that it's nonpolar, it's not that these atoms lose their electronegativity. They still have the same electronegativity. It's just that things cancel out. So with these, they're the same atom. So essentially, it's easy to see nobody's going to be no more positive or negative because they have the same electronegativity. So if you tried to subtract them, that would equal 0, which is less than 0.5 if you want to look at it from a mathematical standpoint. And then here, if you look at it, this carbon still has a delta positive and these oxygens still have delta negatives. So the negative character still resides on these oxygens, but because the molecule is symmetrical, you have the same thing happening on each side. It's just like this, it's just with more atoms. So you have the same thing happening on each side, and they are all going to cancel out. And then if we want to look at this way, this third example is a little bit more complicated with the carbon and the chlorines, but we can make it much easier. So we can draw these in if you really want to see them, and then have the negatives here. But if we look at these two, I'll use a different color to show you. If we look at these two chlorines, they're in the same position relative to the carbon if we draw a line right down the middle. So these guys are going to cancel out mathematically and just electronegativity wise. And then same thing with these guys if we were to draw a line here. And then the carbon's in the middle of it all. So if you were to subtract all of these, which would be really complicated, you wouldn't want to do that, it would equal 0 also, which is, again, less than 0.5. So that's why it's nonpolar. So polar basically means that one end of the atom is more negative than the other, and nonpolar means it's same throughout. I know you can't see that, but nonpolar just means that there's not going to be any partial positives or negatives in that atom because everything cancels out. I feel like this is stuff we've already all gone over, but if we want to look at it again, you can kind of just look at the elements here and see if it's ionic or covalent just based on how that's going to be. The Lewis structures aren't too bad to draw. I'm guessing you're fine with that. But if you want me to do this as an example, you can do it later. I'll just explain the answer for the sake of time. So this is covalent bond, ionic bond. Whenever I see calcium, I just think of it existing as kind of an ion here. And then you have the other -2 here. Same thing with sodium or potassium. Those are usually making ionic bonds. Like NaCl, which is table salt, is like that. It's like Na plus Cl minus. What's another one? KBr would be like K plus Br minus. So you can kind of think of them as two separate things for ionic. And ionic bonds aren't going to be they aren't going to be polar because there's no the atoms aren't connected. Lewis structure is, again, pretty straightforward. I'm guessing she's asking you to draw the transition, or not transition states, sorry. She's asking you to draw the delta positives and negatives. So that's all about looking at your periodic table. And if we remember, nitrogen comes before oxygen in the periodic table. And so if we're looking at this trend, nitrogen is more over here, oxygen's more here, so oxygen is going to be more electronegative. And then when you're drawing an atom like this, and the whole atom has a charge, you can just draw brackets around it to add a charge on the outside. Oh, this is an ugly slide. She used really bad colors for this. I'm sorry. So we already did this, but this is naming. I'm really bad at naming, so this might be tough, but it's just memorization and knowing these processes. So we have to think about the bonds that we have. So first of all, your number one step is going to be identifying, is it an ionic bond? Let me use another color here so you can see. I don't even know what color to use on this. It's so ugly. There you go. Pink will work. That'll show up cool. So if it's an ionic bond, that means it's a metal bonded to a non-metal. And then covalent bonds are non-metals only. So it's going to be a non-metal bonded to a non-metal. Sorry, that was really bad. Non-metal, non-metal. And then this is metal. And they're not really bonded, if you remember. But we'll just say this is positive, and then, I don't think that's how that would work, but we'll just say this is positive, and then NM is negative, and technically they're bonded. But not really, because it's an ionic bond, and this guy, the non-metal, probably just stole the electron from the metal. And then transition metals, if we go back to our periodic table, oh my, so many slides. The transition metals are here in the periodic table, I think. These might be part of it too, I'm not sure. But just check where that is, but you're just identifying where it is on the periodic table. That's the biggest thing. So just make sure you know where all that stuff is. Let's see. Yeah, so if it's a transition metal, then RN. Oh, Roman numerals, sorry. I was really confused. If it's a transition metal, you're going to use Roman numerals to tell the charge. So whatever the charge of that transition metal is, so the charge on the metal, so let's say, so here she splits it up like I do. So the Fe is going to be a +3 because it's bonded to 3 chlorines, ionically bonded to 3 chlorines, and each chlorine has a negative charge. So it's like -Cl, 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 and these guys are all bonded. And so that gives it the +3 charge. Fe is our transition metal, and so we're going to use 3 Roman numerals to designate that. So it's going to be iron, sorry. I'm really tired. It's been a long day. I got up at 6 a.m. It's going to be iron 3, as she has written here, because it's iron is the metal, and then the charge is 3. Sorry, I don't know what she's doing here. And I'm guessing if it's not a transition metal, you would just write the name of the metal. So that's pretty straightforward. Then if it's the non-metal that's part of that bond, so here this would be Cl. If it's, I don't know what this means. I'm sorry. I don't remember that at all. It's probably just chlorine. But you're going to want to check me on that because she's not giving you an example of what that means. But if you have one non-metal, then it means... What? I'm sorry, I don't know what she's meaning. But if you have one non-metal like we do in this example, you use ide. So it'd be chloride, or if we had Br, it would be bromide. And if you're really confused about this, then I can try to let you know, but you can also just Google that. And then, let's see, this is still divided. Let's see. These are just more examples of the same thing. And you can look at those and see why, but this just means that it's all one nonmetal. And then you're going to write it with its charges. So that's kind of what we've already been doing here, like the plus and then the minus. And then you just balance the charges, knowing like what are we gonna, I don't really know what she means by some of this, but I think she just means crisscross reduce. I think she just means that this 2 is gonna mean that there's two PBs, and then 4 means that there's 4 S's, so you like switch that, and then same with this. So whatever the charges are, it's just going to be the opposite for each one. And you can kind of think of that as like, you know, magnesium would have like 1 electron that it's willing to donate to the phosphorus that has a -3 charge. So then you need to fill that whole -3 charge, you're going to need 3 molecules of magnesium. That's a kind of way to reason it out, but if you just remember that crisscross rule, then you'll be fine. And then Pb2S4, if we're looking at that, that's the same as PbS2. So Pb2S4, just divide that by 2, and then you get PbS2. You can probably divide that by 3s too, or like 4ths if you need to. It's just like fractions. So if we did like 2/4, it'd be 1/2. So then you have a 1 here that we just don't show. And then I'll go back to do the covalent, and I'm actually going to clear up all of this on ionic because it's getting really messy on this slide. I just like to write a lot of things to kind of show it, but I'll do the covalent for you too. Let's see. So for covalent, maybe I'll use a darker pink. So covalent bonding is just nonmetals. And what you're going to do first for those, well, our first step is really identifying is it ionic or covalent. But your first step for covalent bonds after that is just naming the first element with a prefix. So essentially what you're doing is you're saying, what's the element that we have first? So here, the first element that we have is nitrogen. And we look at how many nitrogens we have. We have 2 nitrogens, so you're going to use di for that. And then you don't use mono for the first. So if it's the first, you just do nitrogen. Sorry, my Apple Pencil is about to die. It'd just be nitrogen if it was just 1. So if we had like NO4, or you know what, let's do NH4. That's a better compound. NH4 would just be nitrogen. You wouldn't say anything else. Yeah, so just know these prefixes. So di, well, I know di because we use it a lot, but pent is 1. It's all the Latin stuff. Di, tri. I don't remember. I haven't done this in a long time, Jossie. I'm sorry. Okay. Name the second element with prefix and "ide" ending. So you're doing the same thing, essentially. So what you have is, we already did the dinitrogen. It's the same exact thing. So you have oxygen. And then we want to replace that ending. So egen, we want to replace that with "ide." And my pencil is still dying. It's okay. Want to replace that with "ide," so you get oxide. Just because it's the last element. It's the same as this. Our last element has that "ide" to it. And then there's 5 of them, so it's going to be pent for the prefix. So you have dinitrogen pentoxide, and if she gives you this, it says dinitrogen pentoxide, you should know to write out N2O5 for the empirical formula. Oh my. still lots of this. And then this is very straightforward. It's just, you write down what they are. And this is for, like, going backwards, essentially. So you would just write NO, and then di equals 2, mono equals 1. I don't know where she got that from. Oh, it's a different compound. So dinitrogen monoxide. So, and then for the last one, you would use mono. So for the second one, for the first element, you don't use mono. But for the last one, you do use mono for the second compound. And we went through this. It's just a lot of memorization and practice. Practice is the number one thing. I would say if it's the morning before your exam and you don't have a lot of time to practice, then try and find some problems online that you can do really quickly. I'm not going to do these warm-ups. Let's see. What were we struggling with? Yeah, this is good. This is good to do this. That's pretty straightforward. It's just looking at the periodic table and stuff. And then this is just her wanting you to memorize this. This is exactly what we went through in the notes. It's the same thing, and it's just memorizing these processes, and I already explained it. But I can go through these really quick if you want to. So I'm guessing this is what you were saying with once and halves. Use another color again really quick here. So basically once and halves is giving you, it's just this formula that you can use. So for the once, you're talking about how many electrons each atom would want. So here, this 8 comes from the nitrogen. The nitrogen is a normal element, so it wants an octet. And then the 2 is coming from the hydrogens. And the reason that there's a 3 here is because we have 3 hydrogens. And then you add those. You add from each element together. And then you get 14 for that. And then for halves, it's just how many elements do we already have? Or how many electrons do we already have? So nitrogen has 1, 2, 3, 4, 5 initially. If we're looking at nitrogen just by itself, 1, 2, 3, 4, 5. That's what it looks like, and you can get those numbers from the periodic table. It's the number of valence electrons that it has. And then hydrogen just naturally has... She has this backwards. I don't know why she has it backwards of what she did up here, but hydrogen each has 1 electron, and then there's 3 hydrogens. So I would actually write it like this. I would write 3, 1, just to keep consistency. But then you're going to add that up, and you get 8. And then a good way to think of this is that we're just finding out how many electrons we need. So how many electrons do we need to fulfill each octet? So we're subtracting these two, as she shows here, because the number that we want is the total number. And then the number that we have is what we already have. So if we subtract what we have from what we want, then we're going to get the number that we need, which is 6 electrons. Sorry, we need 6 electrons. And then there's 2 electrons in a bond. So, and I'm sorry, my pencil is dying, so it keeps looking like not words. But there's 2 electrons per bond, so we divide the amount of electrons that we have by those 2 electrons per bond to get the amount of bonds that we need. So that's 3 bonds. So we've got NH3, and we know that there's going to be 3 bonds because of that. You can already tell because of what it says here. It says NH3, so I don't really know why she had you do all that math. But that's just how you can calculate it if you're not sure. If she just says you have a ton of nitrogen and a ton of hydrogen, and you're like, how many are we going to calculate? Like, how many bonds is this going to make? How many hydrogens do I need? You can use those calculations for want and have to get how many you need, and then divide the need by 2 to get the number of bonds. Pretty straightforward once you practice. The number one thing with chemistry is just practice, practice, practice. That's what I had to do. And it's okay if the exam doesn't go well or anything. I'm sure you'll do great, but just what to do for next exam is I would say don't study the night before. Make sure that you're studying, like, I had to pretty much study, like, almost every day for chemistry in high school, and I still do, just because it's all practice. It's just like math in that way. And this is the same thing here. Same exact concept. And this is, if you just remember honk rules, which is the HO in C, we could see that carbon is in the fourth. You're already going to know that the carbon normally wants to make 4 bonds. I would say if your teacher wants you to do it this way, you can use this to check, but you don't always need to, and I think honk rules are a lot faster if it's a pretty common element. You can see the same thing here with nitrogen. We have HO and C. This is 3, so you already know that's going to make 3 bonds. Pretty simple. And it seems like that's it. And I know this is a really long video. Sorry if it's super, super long. And my pencil is about to die, so it's probably good. If there's anything that still doesn't make sense to you, please let me know. And you're going to do great. Love you. Bye.